Hi everyone, good morning, good afternoon, good evening, wherever you are. We're back again with our Snyk Live, and this time we have a very interesting topic to discuss. Wherein Snyk actually team has developed a plugin for Burp Suite, but I would just keep the suspense going on because that's we're going to be talked about with my friend Elliot Ward, who is part of our security R&D team, where they keep researching new topics, new tools, new features, and whatnot. So let me bring Elliot and let's get to know him more. And then we will deep dive into the topic which we have today. And the topic is around SocketSleuth. So let me just bring him in. Hi,
Yeah, hi
Elliot.
there, Vandana. Hi there, how
I,
are you?
I am good. How are you?
Yes, very good, thank you. So yeah, thanks for having me here today.
Thank you so much for agreeing to be part of it and creating this beautiful plugin for Burp Suite. And uh, we just want to know about you first, and then how did you think that this can be important? And we would love to get deep dive into the plugin itself.
Yeah, no, that sounds great. So yeah, I mean, my name's Elliot, and yeah, I'm a security researcher here at Snyk, and for yeah, most of my career I've been in kind of on the pen testing side, so performing penetration tests and mostly with a focus on application security. Um, for yeah, the last 8 years or so, and yeah, recently, well, not recently, joined Snyk about 18 months ago, where I've been, yeah, in the security labs team, where we undertake a variety of security research topics, kind of with a focus on developer security. So anything that can have an impact on, uh, yeah, the life cycle of a developer. So the way that they operate, to the plugins or ecosystems that they use for package management, or the packages themselves. So yeah, we're just trying to find new ways to attack applications, or overall improve the security of modern web applications.
Totally amazing. Totally amazing. Now, let's get started with the Socket Sleuth. We really want to know what it is and how it works. So, let me get your screen in fast. Here we are.
Yeah, perfect. So I mean, yeah, just before we kind of go into what SocketSleuth itself is, I mean, I think it's important to kind of set a little bit of background, maybe for those who aren't familiar with what WebSockets are and how they work. So kind of just to go through, I mean, just yeah, we've already discussed this a little bit, but yeah, I'm based out of Zurich in Switzerland. So yeah, that's kind of me and what we're going to cover today. So I mean, we'll go over kind of an introduction to WebSockets first, so we're all on the same page, and then we'll look at some of the kind of the threat landscape for WebSockets. We'll go over a little bit of our research, and this is kind of where we got the inspiration to build SocketSleuth, because yeah, we found some of the existing tooling could be improved as we felt, and then we'll give a demo of the new Burp extension, show you where you can get this, and then conclude.
Perfect. Let's get started. Thank you so much.
Perfect. So, firstly, I mean, if you've not heard of WebSockets are essentially a low latency, efficient bidirectional communication channel that's built on top of regular HTTP. So, what this means is that we have a normal HTTP request, that we have some special headers that cause the request to get upgraded to a WebSocket. And this diagram kind of helps us to understand this. So, we'll send the WebSocket handshake request, which is yeah, basically a normal GET request, and then the server will set some headers back that will basically upgrade this request or the response to a WebSocket connection. And once this has been established, we can then bidirectionally send and receive messages within this stream that's been set up over the same TLS connection. So this allows us to send multiple real-time messages without having to try and do kind of hacky techniques like long polling, or where we send multiple HTTP requests to try and get this data in a what feels like real time, but is actually lots of different requests, and each one of those then requires its own HTTP request, its own TLS handshake. So obviously this is a lot less efficient and has a higher latency than what WebSockets provide. Obviously, this can still be fairly complex to set up in some cases, and there could be some reliability concerns. I mean, if we have some firewall that's tearing down connections after a certain amount of time, or the server doesn't have many resources and it's got to keep all of these connections alive. So, I mean, it's not perfect for every scenario, but yeah, we'll have a look at this, and we'll be looking mostly on the security side to see, okay, like what are the security implications of using WebSockets. So let's have a look. So first of all, we have the WebSocket handshake, and with the WebSocket handshake, as I said, it's a normal HTTP request, but what we have here is this connection upgrade header, and then this is combined with two other important headers here. So we have the sec WebSocket version, where the current version is 13, and then a sec WebSocket key, and this is just a random value that's generated by the client and sent with the WebSocket handshake request. On the server side, when we receive this request, if the server agrees and would like to speak WebSockets, it will first respond with a HTTP status code of 101, which means switching protocols. And then it will set a couple of additional headers in the response. So we have the upgrade header here, which we set to WebSocket. And this is followed then with a connection header of upgrade, and then the sec WebSocket accept header. What the sec WebSocket accept header is basically it will take the sec WebSocket key that was sent by the request. It will concatenate this with a static constant, and then it will perform a SHA-1 hash, and then base64 encode this. And this basically allows us to guarantee that both of the server and the client are ready to start speaking WebSocket. One thing that's important for us to kind of understand is that we don't just send data to and forth. We basically encode the data into what we call WebSocket frames. So, I mean, it's similar to a TCP frame at some degree, but it's a little bit simpler. And we have a couple of opcodes that we can have here, which will go into this opcode part of the header. And basically, we have the continuation frame, and this is responsible for if we have, for example, fragmented frames. We have then text frame, which is specified when we want to send text data, and then this will be represented as UTF-8. Then we have binary frames, which is good if we're sending arbitrary binary data. So, I mean, it doesn't have to be kind of strings or JSON format. We could be sending, raw images or video streams or any arbitrary binary data. And then there's a couple of control opcodes. So these are more responsible for managing kind of the life cycle of the WebSocket session. So we have the connection close opcode, where if one peer receives this, then they should, by the RFC specification, close down the connection and finish speaking WebSocket. And then we have kind of ping and pong frames, and this is basically to test whether the other peer is still responsive. So if the client sends a ping to the server should respond with a pong. And if it doesn't receive a pong within some certain time frame, then the client may decide to send the connection close, which would result in that WebSocket being torn down. Another important concept for us is the concept of masking, and this is basically to prevent any intermediaries, such as caching proxies, web application firewalls, etc., from misinterpreting WebSocket frames as HTTP content. And this will help us prevent from such attacks like request smuggling and cache poisoning. And with this, we basically mask client to server frames. We generally don't mask in the reverse direction. And this is done by basically the client will generate a 32-bit random masking key, and then this will be XORed with each byte of the data payload in a circular fashion. And kind of on the table here, we can kind of see how this might look. So we have here the original payload in its ASCII format, and then its hex representation of this. And then we have the masking key bytes. So we XOR the 34 with 12 to get the mask data byte. And then we go forward. And then once we hit the end of the 4 bytes of the 32-bit masking key, we then start again from the first byte. And then we do this until we've got our complete encoded WebSocket payload. And kind of what does this look like on the wire? So, I mean, if you open up Wireshark and have a look at a WebSocket frame or connection, you'll first see, obviously, the handshake request. This will be then followed by the handshake response. And then we can start seeing the data frames going back and forth. And in this case, the client sent the first frame. And as we can see, the data inside here doesn't appear to be at least readable in a human format. And this is because it's been masked. But then when we see the server's response, we can see that the server to client frame is unmasked. And yeah, we can actually understand this data by looking at it. So let's first have a look at kind of one of the most prominent WebSocket issues that you may have heard of, called cross-site WebSocket hijacking. And this is kind of a result of that WebSockets don't implement their own authentication mechanisms. But this should be okay, right? Because we have, the server has already implemented some sort of authentication mechanism through probably a session token that's being stored in a browser cookie. And then the same origin policy is there, right, to protect us. So this should prevent one origin from reading and writing to a cross-origin WebSocket session. But we'll have a look and find out if this is actually the case. So to first kind of understand this, we need to look at what is the same origin policy and how does this work. So the same origin policy is basically a security mechanism that's implemented by the browser, and it restricts what origin or domain or website can access resources on another origin or website. And this can be relaxed through CORS, which is the cross-origin resource sharing. But this isn't the subject of what we're here today to talk about. But essentially, these restrictions apply to what is called an origin. So an origin is defined by a scheme, a host, and a port. So let's have a look and just see if we have a couple of different origins and they're trying to speak to each other, what the results might look like. So, I mean, if we have Snyk.io and we try to access google.com, this will not be able to read the data on google.com because it's a different domain, and this will cause the origin to be different. And similarly, if we have Snyk.io trying to access app.snyk.io, even though this is the same domain, the subdomain is different. So this is also not considered the same under an origin. Likewise, different protocols, so a mismatch of HTTP to HTTPS is also considered a different origin, and different ports are as well. But when we have Snyk.io trying to access Snyk.io/API/user, this is allowed under the same origin policy because the origin is the same. So then the browser can send data and read that data at will. So kind of let's look at what this would look like under a normal HTTP scenario. So if we go to evil.io in our browser, this will return a page to us and say that this page has some malicious JavaScript. And that malicious JavaScript then opens up an XHR or an AJAX request to my profile on Snyk.io. What would happen in kind of a typical case if we're ignoring, for example, same site cookies, which makes this a little bit more complex. But historically, when you make this request, the cookies would be sent along with the request, and then the browser would send back the response. But the server would send back the response to the browser. But what's important to understand is that the browser will not release that response to the application or to be allowed to read this. So if you looked in the network tab, you would see that, okay, the request and the response has been sent. But then if you had the console of the browser open, you would see a CORS error. and any JavaScript from evil.io would not actually be able to access that information. So we're not going to end up leaking any information here. But as I've, one of the key things to understand here is that the same origin policy does not apply to WebSockets. And then this introduces the class of vulnerability called cross-site WebSocket hijacking. And we'll have a look at what this looks like in a second, but it's important to note that just because the same origin policy doesn't apply to WebSockets, it doesn't mean that everybody is vulnerable to this. There's certain things that can be done to make WebSocket connections safe, and we can perform additional authentication during that handshake. So what's kind of common is to append in the request somewhere an additional token that would not be sent by the browser automatically. So when that handshake is happening, the server side will check for that additional token, and if it's not present, it will reject this handshake upgrade. Similarly, we could also perform this authentication once the WebSocket connection has actually been established. So it could be that the first message of the WebSocket communication itself is a login message where a token is provided, and only after that will the server actually perform any actions. And then we could also do kind of a manual origin check. So even though the same origin policy isn't being applied here, the origin header itself is still submitted. So we can look at that origin header and check it against an allow list to see, okay, is this origin allowed to open a WebSocket connection to my server? And if this is the case, then we could allow or reject this WebSocket connection. So kind of when we consider the same origin policy in relation to WebSockets, this is kind of the view that we have. So compared to the previous example, when we make a request to evil.io to get the web page that has our malicious JavaScript, this WebSocket or this malicious JavaScript will go ahead and instantiate a WebSocket connection to Snyk.io/ws, and then we will happily perform the WebSocket upgrade. And once this has happened, we will have a bidirectional WebSocket established, and both the client and the server can read and write to this WebSocket connection. So the evil.io domain is actually speaking to a WebSocket on Snyk.io, and we're not being restricted by the same origin policy. So this can lead to some potential downfalls and lead to some dangerous situations. So one thing that we did in the Snyk research labs team is we wanted to kind of look at how prevalent are cross-site WebSocket hijacking issues. So we had a look, and we first identified some popular candidates that are using real-time applications across kind of enterprise applications and open source applications. And once we had kind of a list of applications that we could look at, we checked to see, okay, are they using WebSockets? And if they were they using cookies to handle the authentication instead of an arbitrary like authorization header, for example? Because the additional arbitrary headers would not provide the automatic submission of that header, so it wouldn't be possible to do that cross-origin. And then we needed to check whether or not there was any additional authentication checks, for example, during the handshake or inside the WebSocket. And then we want to check whether or not there's any manual origin checks taking place. And then other than this, there are some other kind of things that can make WebSocket hijacking harder to exploit, such as same-site cookies, which restrict under what circumstances the cookies are submitted with the request. It's a fairly recent addition to browsers, and it will prevent many cross-site WebSocket hijacking attacks. But in all of the examples that we reported to the vendors, we were able to bypass the same site cookies and have a fully exploitable scenario. So to kind of just look at some of the different applications that we looked at, this is not the complete list. This is just for kind of illustrative purposes, but this is a subset of the applications that we looked at. And we first checked to see were the WebSockets there? Are they performing the origin or additional authentication checks. And as we can see, some of these were not doing these additional checks. And I mean, this doesn't necessarily mean that these are exploitable. As I've said, there may be kind of same site cookies, and in the case of some of the applications, I mean, 1Password as an example, we didn't actually see any messages within those WebSocket connections. So at least when we checked and under the conditions that we reviewed this, there was nothing to hijack. So that was not exploitable in that case. But kind of on some of the results that we did find, yeah, many of the kind of online versions of IDEs, these were using WebSockets to provide the real-time updates, and these were, in most cases, we found vulnerable to WebSocket hijacking. So we have a few kind of issues here with kind of Gitpod, the VS Code server, and Daytona, which was formerly known as Code Anywhere. And yeah, these were vulnerable to WebSocket hijacking. In some cases, it allowed it a full takeover of the IDE, which was leaking then, the customer's code, for example, which is not ideal. A couple of other examples. I mean, we had some XMPP client, NodeBB, which is a popular node-based messaging board, and then some other things like an ERP product, a ticketing system, and a course management system. And these ones are still in disclosure, so we can't go into the details of what these are, but we'll probably have another blog post following up once these have been fixed and disclosed. So kind of once we now understand how WebSockets work and the fact that the same origin policy doesn't apply and leads us to this concept of WebSocket hijacking, let's have a look and see how this looks in practice. So here I have kind of a very basic application. We have just a login page with some where we can log in, and let's go ahead and log in. So I mean, we can log in as Alice, and it's a basic chat application. So it's just for kind of illustrative purposes, but we can go and type hello, and this brings this up here. And what we can then do is we have our WebSocket hijacking example here. So basically with this, it's a separate domain as we can, or separate origin. In this case, it's 9092, and over here we're 9066. So under the concept of the same origin policy, this is a different origin. But if we go ahead and try and connect to this WebSocket, we see that this was successfully connected. And then if we can go ahead and say, you have been hacked, we can go ahead and send this message. But then if we go back to the chat application, we can see that this message has been sent on behalf of our victim. So Alice never sent this message. So like she's obviously very concerned here and wants to tell everybody that that was not her. But then when we go back, we can also see that the attacker has been able to see this information. So when we perform this WebSocket hijacking attack, we can both not only kind of send arbitrary data to the vulnerable target, and similar to in a cross-site request forgery attack, we can kind of send data. But what's interesting is that we're also able to receive data too. So it's I like to think of it as a mix between a cross-site request forgery and a cause misconfiguration bug. Take that as you will, but it's a very powerful vulnerability that can leak and provide a lot of access to functionality of the website, depending on what the application is doing. So obviously, in this case, it's just a chat application, but it could be that, I mean, go back to the case of the IDEs. In those cases, it was possible to see all of the information that was being typed, any terminal commands that were being executed. These could be read, but it was also possible to inject arbitrary commands to the terminal because the IDEs provide the terminal functionality to allow the developer to execute commands as they need to do their job and obviously, in those cases where there's a WebSocket hijacking issue, this leads to an RCE on that remote workspace. So it can be quite significant. So this brings us on to kind of other issues. So I mean that's one issue specific to WebSockets, but this isn't the only problem that WebSockets can be susceptible to. So we may be passing some JSON data within the WebSocket. We may be passing XML, but when we're doing this, it's still just some data exchange, and the server and the client need to perform some logic based on the information that they send and receive. So this can lead to kind of all of your traditional kind of vulnerabilities. So we may have authorization bypasses, there may be logic bugs, there may be crypto flaws. So like any normal vulnerability that we would test for, we also need to test for this in a WebSocket. But the problem is that the tooling for testing WebSocket applications at the moment is fairly limited. So there are some tools out there. I mean, we have some tools that are more similar to Postman, for example, for HTTP, that allow us to just connect to a WebSocket and send and receive messages. So tools like WebSocket King and Hopscotch allow this, but these are not security-focused tools. So it doesn't provide some of the more advanced features for security testing, like fuzzers or kind of just these. It's just a very basic tool. And then we have OWASP SAP, and this is a great proxy, but it's not as popular as Burp Suite, so not as many testers are using it. And also with that, there's not going to be as many people writing extensions for ZAP as in comparison to Burp Suite. But then the problem with Burp Suite is that it lacks currently some of the automation features for WebSockets. So when we compare the feature set that Burp has for normal HTTP requests, it's not at the same standard that it has for WebSockets. So we don't have the Burp Suite intruder. The match and replace tools can't be applied to WebSockets. And then this generally creates a workflow that's not as intuitive for testing testing a WebSocket application as compared to when we tested like a normal REST API via Burp, for example. So this led to us building our new Burp extension called SocketSleuth. And we chose to build this for Burp because it's the tool that we use the most when we're testing kind of web-based APIs. And we feel that most of the community is also using Burp Suite. And they recently introduced the new SDK called the Montoya API, and this includes better support, or it includes support for hooking into the WebSockets for the first time, which has actually made it possible to build extensions for Burp Suite. So, I mean, if you currently open up the Burp application store, you won't find any WebSocket extensions because historically there was never an SDK to enable this. But yeah, this is now there, and yeah, hopefully soon this will be available in the BAP store. It's midway through the submission process, so it should be there soon. But we can already use this as we'll show in a moment. And kind of some of the initial features that we have here, we have a new view for viewing WebSocket information within Burp. We have an intruder style fuzzer for WebSockets. We have a feature similar to the plugins Authorize and Auto Repeater, which allow automated repetition of HTTP requests, but we're doing this for WebSocket messages, which allows us to find issues with authorization. And then we have the match and replace rules. So although this is a limited feature set for now, it's already quite powerful, and we found this incredibly useful during some of our research into WebSocket-based vulnerabilities. So now let's have a look at the extension. So if I pull open Burp, here we have kind of the SocketSleuth interface here. On the left-hand side, we can see our different WebSockets. And on the right-hand side, we can see the handshake associated with each WebSocket. Obviously, this is both for the same application, so these look kind of similar, but we can tell that it's different by the different WebSocket key. But then inside, we can see all of the messages that were sent and received within this WebSocket. So if we remember when Alice said hello, the first message was there. And then this is the server sending to all of its clients that Alice has said hello. And then, yeah, we can see all of the various messages. And if we compare this to the normal view of Burp Suite for kind of working with WebSockets, it's a little bit more contrived to use. So we can see in the WebSocket history tab, we can see all of our messages, but we don't necessarily know at a glance for which WebSocket each message is for. We do have this WebSocket ID field over here, but it's not necessarily clear when you're on this page because you can't see which WebSocket ID is belonging to which request, for example. And also we don't see the WebSocket handshake. And if we want to see the WebSocket handshake, we have to go over to the HTTP request and look for status code 101s, and then we can go ahead and actually see these handshake requests. Whereas, yeah, in our new history tab inside SocketSleuth, we've tried to make this a bit easier to see, where all of the information is kind of visible at once. So let's have a look at kind of one of the other features that we have within SocketSleuth. So if we go over to here, we have yeah, a basic application, and maybe we want to try to brute force the login of this. So obviously we see here that we have invalid credentials. So let's go over to Burp Suite and look to see what we saw. I don't think that was set up properly. Let's hope that we see this in Burp now. Yes, we do. So over here we can see that, okay, we've established a WebSocket. Here's our handshake, and the first message was when we tried to log in. So we have user one, we tried the password hello. So in Burp Suite, we can go ahead already with the WebSocket tools that are already present, and we can do manual repeating. So we can go ahead and try to send a request manually. My password, let's try this. But it's very manual, and we can't, for example, like we can with HTTP requests using the intruder, provide a big list of potential passwords for this to automatically try. But SocketSleuth does allow us to do this. So we can go ahead here and we can right click and we can click send to WebSocket intruder. Once we do this, we have a couple of different options here. So at the moment, we only have two different attack types. We have one that's specific for method discovery of JSON RPC messages. So if we wanted to find maybe additional functions, this would allow us to do this. And we have kind of a basic word list of yeah, potential JSON RPC message types that we've seen in the past. But you can add to this by pasting from an existing list, manually adding here, or kind of, yeah, clearing this. But then we also have the sniper, and this is very similar to the existing sniper that we have in Burp Suite. And this allows us to basically set a payload insertion point. So we can go ahead and do this. And then what this will do is once we give this a list, we can also give it a range of numbers at the moment. We will be adding more payload types in the future. But for now, these are kind of the two ones that we use the most. So we added these first. But yeah, once we have the simple list, we can then provide, for example, a list of potential passwords. And this will allow us to, yeah, fuzz this password field until we find or don't find a response. So we can go ahead and first of all select which WebSocket we would like to actually use the intruder on. So we go ahead and select the one that we would like to. We can also add a minimum delay or specify a delay between a min and max range. And we can also specify the direction to send these messages. So it could be that we're trying to fuzz data coming from the server to the client, but in this case, we want to fuzz the login mechanism. So we're going to go from client to server. And then we'd need to put in some, yeah, potential passwords to try. So we can go password, password one, user one, pass one. So we can go ahead and try this, and then once we're ready, we can just go ahead and click Start Attack. And this has gone ahead and basically sent all of these, replacing the payload position with the values from our list, and then showed us the response. So in this case, when we have an invalid response, we see that the result is null. So we can basically go ahead and check to see, okay, we have result null, result null, result null. But this one's different. Here we have result one. So if we go back up, we have user one and pass one. So it's possible that the password for this could be pass one. So if we go back to our login form, we can go ahead and try pass one, and click login, and that worked. So this is great. So this allows us to do some kind of basic fuzzing with payload lists. So if you combine this with some of the existing great fuzzing lists, like sec lists, for example, we could easily use this for automatic testing for SQL injection, or any other kind of vulnerability where we may want to try a large list of values, and then watch the responses to see what differences there are. So this is one of the kind of powerful features, and it's provides the same kind of impact on testing as the intruder does, for normal HTTP requests. That's very useful. And one of the other things that we also thought would be quite useful is something to help with authorization testing. So basically here we have the WebSocket auto repeater. So if we go ahead and create a new tab, what this one allows us to do is basically we can specify two different WebSockets. So we would specify one to be the source and one to be the target. So if we do this, go ahead and do this. We basically have two people logged in there, and we can specify one to be the source and one to be the destination. And then we have what's called the direction here. So this will be either client to server, server to client, or bidirectional, which will work for both. And when we click this button here called activate, what happens is that it will take all of the messages from the source socket in the direction of client to server, and it will then repeat that message. So it will it will look at the WebSocket 4, and it will send that same message down WebSocket 4. So as you can imagine, this will allow us to perform authorization testing far easier, because we won't need to be manually kind of copying the names of certain resources into the session of another user to check whether or not it's checking to see if I have the permissions or not. This will just go ahead and automatically send every request down the WebSocket of another user, and allow us to test this. So when we kind of set this up, we log in with we set up two browsers, one logged in as user A, one logged in as user B, and we set the source and target appropriately, and then hit the button, and then we can go ahead and perform any actions. So we may search for a username, user one, and then when we go back here, this is actually sent down the other WebSocket the same message. So we can see there that we've done a search for user one. In this case, it's not going to provide us anything because this functionality is also available and unrestricted to the other user. But when we're testing a more complex application, it's very easy to find bugs using this, especially as the existing tools for testing WebSockets haven't really allowed for this kind of automated testing. So we're finding quite a lot of WebSocket issues relating to authorization using this. And then we can go over to kind of the last part here. So we have interception rules. This will automatically trap a request using the burp intercept. So if we want to automatically modify something when a certain criteria has been set, we can go ahead and do this here. This is basically just using contains, does not contain, or an exact match. We specify the direction and then the condition, which is just a string. And then we also have WebSocket match and replace rules. So again, it's very similar to how this works for normal HTTP requests in Burp, except we're able to specify the direction. And this supports regular expressions, basic strings, and also ASCII strings. And the ASCII strings are quite useful if we want to do a match and replace on some binary data. So we can then specify kind of a string of bytes, where if we see this string of bytes, replace it with this string of bytes. But kind of for the purposes of this, we may, if somebody types the word dog, if we want to change this to cat, we can go ahead, click this, and then if we go back to our application, let's go to the chat, and then we can type it'll be dog, hit send, and then this has already been changed to cat. So, I mean, it's a very simple feature, but it's very powerful. I mean, say that you're doing some testing and you want to check how it's handling names of the users or something, you can automatically change your username to admin whenever it's sent to the server and see if there's any any of the logic that's just blindly taking that data from the message itself. This is quite useful for this, and I was quite shocked to see that the match and replace rules here under for normal HTTP requests don't actually allow you to specify this for WebSockets. It's only in requests and response, which is why we added this feature for SocketSleuth. So yeah, I think that gives a good intro into SocketSleuth. You can go ahead and try this. So we have this available on our GitHub. It's in its early stages, so we are very welcome to hear feedback. We're open to contributions. We have all of the licensing and everything on the GitHub, so you can see how you can contribute to this or use this if you would like. And yeah, we'd love to hear your feedback. And yeah, thanks for allowing us to share this today.
Yeah, thank you so much. I think it was amazing. And I am sure a lot of people will reach out to you afterwards. So, what is the best platform to reach out to you? Would that be LinkedIn?
LinkedIn would work. Or I guess I have Twitter as well. I don't really use it that much, but this would also be fine. Let me just put this in the comments, and then you can figure out how to look at this.
Sure, absolutely.
But yeah, other than this, LinkedIn works too.
Mhm. Perfect. So we would be keeping that in the chat. And for everyone, if you have any questions at any given point of time, please feel free to reach out to Elliot, and we'll be more than happy to answer any of your questions or take up any questions. Thank you so much, Elliot, for joining me today. It was wonderful to have you.
Oh, yeah, thank you very much.
Yep. Thank you so much, and have a great day, everyone. Take care. See you again.